Hello everyone, my name is Raúl Hugo Morales, and today I'm here to describe a prolific technique to stimulate wells that produce oil and gas from weakly consolidated reservoirs, known as case-hole frac-packing. Typically, these rocks have Young's modulus between 300,000 and 900,000 psi. Poisson's ratios between 0.2 and 0.3, porosities greater than 20%, and permeabilities ranging between millidarcy to darcy. Examples are the fine-grained Pleistocene-aged rocks from the Gulf of Mexico. FracPack candidates: extended reach vertical and deviated wells, reservoirs with expected large drawdown pressures, reservoirs with the possibility of early failure, wells where the surface facilities are unable to handle fines, and wells where it is expected early water breakthrough. A typical frac-packing procedure consists of pressure testing to find and fix tubing leakages, pickle the work string to clean gunk, acid and solvent treatment to condition near wellbore region, calibration treatment to estimate fluid efficiency and closure pressures, design of the main treatment using a pump schedule generator, pumping the main treatment and reversing out residual slurry. This diagram shows the downhole FracPack equipment. During pumping, the flow path is in the set down circulation position, meaning that the fluid pressures acting in the lower annular section, orange color, are also acting in the upper annular section, blue color, as these sections are connected by the crossover ports 1 and 2. Thus, a pressure gauge set below the surface valve can monitor the true bottom hole pressure behavior. Because the surface valve is closed, fluid can only exit through the perforations. This other diagram shows the fluid path. When pumping starts, the fluid, which consists of a clean fluid known as pad, followed by a propant slurry, flows from the surface lines through the work string, through the lower annular section, and through the perforations into the reservoir. The increase in fluid volume triggers an increase in fluid pressure. At the threshold pressure, the rock is fractured, and two collinear fractures propagate following a path normal to the minimum in situ stress direction. Fracture lengths are mostly defined by the pad volume, and fracture widths are defined by the propant volume. Typical bottom hole pressure signatures are shown in this figure. Point 1 is the breakdown pressure and the beginning of fracture propagation. Point 2 is the end of fracture propagation and the beginning of fracture packing. And point 3 is the end of fracture packing and the end of the treatment. Generally, soon after the propant reaches the perforations, yellow line, the propant bridges the fracture contour and fracture propagation stops or decreases while fracture packing starts. This figure shows typical bi-wing fracture lengths and propant widths. Another feature that must be considered is the poor bonding between the cement and the rock, That results in a second microannulus, which is also packed with propant. This microannulus triggers the initiation of bi-wing fractures, normal to the minimum in situ stress direction, which propagate parallel to the well axis, ignoring the perforation orientations. Magnolia Field example. The Magnolia Field is a tension leg platform in about 4,700 feet of water in the Gulf of Mexico. Highly inclined wells targeted multiple zones of the reservoir. We are focusing here in a well which is highly deviated with a long perforated interval. The bottom hole pressure measurements are shown here. The left plot shows the gamma ray for this well. It shows two sands separated by a 50 feet shell within the 571 feet perforated interval. 5 bottom hole pressure gauges were placed within the perforated interval. The horizontal slopes within interval 1 to 2 indicate fracture propagation. The increasing slopes within interval 2 to 3 indicate fracture packing. Since all gauges show similar pressure behavior, we can conclude that the entire interval was fractured. The bottom hole temperature measurements are shown here. The right plot shows the readings of the temperature gauges. During fracture propagation, interval 1 to 2, the temperature plots of the upper gauges show a steeper declining slopes compared to the lower ones, indicating more fluid flow in the upper sections. During packing, interval 2 to 3, the temperature plots of the upper gauges show a steeper increase in slopes compared to the lower ones, indicating that the temperatures are tending towards an equilibrium level because fracture propagation has stopped. Radioactive tracers were run to visualize the propant coverage. The slurries with propant concentrations from 0 to 7 ppA were tagged with scandium, yellow color in the plot. The slurry with 7 to 12 ppA concentrations were tagged with iridium, red color. Note that the slurry tagged with scandium covered inside and outside the entire annular section, while the slurry tagged with iridium didn't pass below the lower sand. Possibly, the fracture width within the lower sand was narrower. FracPack skin data. Generally, permeabilities around a wellbore are different from the permeabilities of the formation. The zone with altered permeability is called a skin, and its effect on the flow behavior of the well is called a skin effect. Wells with smaller skin values are less damaged than wells with larger skin values. This plot shows FracPack skins for 90 wells from published pressure buildup data. The average skin is 6.2. The plot shows that skins increase with increase in KH values, where K is permeability and H is reservoir height. The standard deviation curve for the 90 wells is shown here. The lower values are close to -5 and the upper values approach +35. Thus, the data is skewed to the right of the mean value of 6.2. About 63% of the skin values are smaller than the mean, while 37% are greater. This concludes this presentation. Thanks for your attention.